talking about
recording in progress.
I'm going to talk about axions accelerating the universe through PT-symmetry. So the outline of my talk is about lambda CDM, which is the standard model of cosmology, and the late era acceleration evidence from different cosmological sources, which is challenging the lambda CDM. And in particular, I shall talk about the DAISY experimental results and related lambda CDM shortcomings. So given these so-called tensions which we're having in cosmology, it is perhaps a time for a paradigm shift to understand the late time acceleration of the expansion of the universe. What I shall be talking, and I'm particularly excited to talk to this audience here who are experts in renormalisation group, is we have some rough idea about how PT non-Hermitian phase of gravity could arise through renormalisation group. It is in some ways somewhat daring, but nonetheless is still a rough idea, and there is a lot to be done. This paper is based on two articles. One from December of last year with Eric Chen and Nick Mavromatos and myself. And the first paper, which started everything off with Nick Mavromatos and myself, is from Physical Review D in 2024. So before I go further into experiments, since the experiments do depend on the theory, and I'm going to give a theoretical talk, it's actually not a bad idea to talk about the lambda CDM and just remind you, this is the standard model of cosmology and what it is based on. It's based on general relativity and the Friedmann equations governing how the universe expands. The universe is assumed to be homogeneous and isotropic on large scales. The components that go into the model are baryonic matter, 5%, 27% cold dark matter, and 68% something like dark energy cosmological constant. It's been a very successful model, no doubt about it. It's got only six fundamental parameters. The CMB temperature fluctuations match extremely well with its predictions. The large-scale structure, the web of galaxies and filaments, is well reproduced. Big Bang nucleosynthesis, primordial abundance of hydrogen and helium, again, in good shape with the model. The universe is aged 13.8 billion years, again, in good shape with the model. So, what's the problem? The problem seems to be that since experiments are getting more and more refined, cracks are appearing in our understanding. In particular, there is something called the H0 Hubble tension. So what's happening is that the experiments from the early universe, the CMB, they are being used with the lambda CDM model to predict what's going on at our current time. And of course, in addition, there are some distance ladders of kind of our current time understanding. And so these measurements of the extrapolated Hubble constant for today are not agreeing with the experiments from standard candles that are being done in more recent eras. And so that's the tension. And you can see from these figures here, the gray are the CMB and the blue are the Cepheids, which are the kind of more modern era candles that people use. And the difference is actually shown in the graph below it, and it's about the statistical significance is about 5.3 sigma, which is saying something like 1 in 3.5 million chance that it's just statistics. So it's indicating that maybe there is something that we have to worry about. And the figure on the right-hand side is just saying the various groups, including the DAISY, the dark energy spectroscopic instrument, which has been very active recently. And you can see again, there is a discrepancy between what CMB and the lambda CDM arguments are with the latest experiments. So that's the tension. So is this the only place where this is happening? No, there's also another tension, the S8 tension, And this is to do with the large-scale structure of the universe. You can see here just a simulation of the cosmic web. Bright filaments and nodes are where galaxies and galaxy clusters form. And there is a quantity called S8, which is related to the clumping. This is not expansion anymore. It's to do with the clumping in the universe. And S8 is made up of sigma 8, which measures the amplitudes of matter density fluctuations and scales of 8 megaparsecs. And omega m is the total mass density of the universe. And so again, when you look at this and look at the CMB Planck data, and then look at what's happening and use lambda CDM to see what should be happening now, and look at the recent experiments of things like DAISY, there's a discrepancy. The CMB is talking about 0.83 for S8, and the weak gravitational lensing stuff of more recent era stuff is 0.76. So this is not as sharp an effect. It's a 3 sigma effect, but nonetheless, again, it's a form of tension. So the other thing about the DAISY results is that they tried to fit not using lambda CDM with lambda constant, but having a lambda which is varying with time, and that seems to be having a better agreement. So again, this is indicating maybe that the lambda CDM model needs revisiting, and so that's where we are at the moment. I just want to show this graph. This is again showing how the lambda CDM model overall has been very successful. It's managed to discuss all these cosmic microwave, dark ages to first stars, etc., etc. But if you see at the bell, this bell shape here, there is a flaring at the end of the bell shapes, which is showing that the dark energy is currently pushing the universe apart. So again, there is a increase in the expansion rate of what's going on, which is not what you'd expect from lambda CDM. So where are we? What do we do? So one thing is that there could be experimental errors, and 5 sigma sounds pretty strong kind of belief in the experimental findings, but nonetheless, the S8 was only 3 sigma. So there could still be a room for further refinement of experimental procedures. But the intriguing thing that I would like to talk about here is that possibly, this is indicating some sort of new physics, okay? Where we have a dark energy which relaxes or changes over time to explain the expansion sped up more than expected. So I've already indicated to you about the lambda CDM model. It's actually not quite a model. It's a parametrization. And so as a result, it's got 6 parameters. In terms of a fundamental theory, the cosmological constant, if you believe in quantum field theory, which is a very successful way of studying theoretical physics and physics in general, that quantum field theory would give for the vacuum energy density some value of lambda, which is 120 orders of magnitude too big. So clearly, if you want to embed the theory into a more fundamental framework, it's obviously challenging. And so that's where we are. And so now I want to get on with the rest of the talk. So where do we go? Lambda CDM is a bottom-up fit. Okay, so what are the things for a top-down origin? So string brane theory could be potentially a top-down origin for the components of dark energy and inflation. Now, everyone realizes that string theory is potentially a theory with profound insight, but nonetheless, it's in 10 dimensions, and we have a great deal of difficulty in kind of reducing and getting effective theories in 4 dimensions. Now, one of the things about when you deal with gravity, and remember, lambda CDM had general relativity there, we have diffeomorphism invariance. And so anything that we're trying to get, which is going to be a top-down theory, should have diffeomorphism invariance. Otherwise, we really are perhaps not talking about gravity. So, so essentially, one of the things about the string theory models is, etc., is that this is what Alvarez, Gomez, and Witten found years ago, that there were gravitational anomalies, which basically mean that diffeomorphism invariance is not being respected. So that isn't very good. So then, again, quite some time ago, about the mid-1980s, Green and Schwartz, who are pictured here, they said, well, okay, we need to cancel these anomalies, and we need a new field, which they call the Kalb-Ramond field, okay, which is in 10-dimensional supergravity. It's B mu is a 2 form, okay? So that message from there is that, okay, you want to get an effective theory, you want to have diffeomorphism invariance, so you probably should have gravitons, obviously, and then you should also have the Kalb-Ramond field. Now, so we want to have a theory which is kind of based on those ingredients, and obviously when you have when you go down to 4 dimensions, there are all sorts of compactifying issues, etc. What happens is that the B mu nu, which was a 2 form, becomes dual to a scalar d mu b. Okay, so I don't know whether you can see my pointer here. D mu b, which is given in terms of the field tensor. The field tensor H nu rho sigma is the field tensor associated with the gauge field B mu nu. That's why it's got one more tensor index. So essentially, our starting point will be to look at axions, these Kalb-Ramond axions B, which are not related to compactification axions. They are really axions related to the gravitational sector, and try and see whether a theory based on these ingredients have interesting properties. Now, these ideas have already been taken up by one of my co-authors, Nick Mavromatos, and his collaborators, Solar and Basiliakas. They have produced something called the stringy running vacuum model, which uses the above string theory to probe the vacuum in the primordial universe. That means before inflation has finished, okay, as an effective theory. So they have a motivation which is similar to the motivation that we have, but although we start off with a 4D effective theory, they go in directions which are not the directions that I'm going to be talking about there. But nonetheless, we need to know some of the features that they have in the way they've done things, so that our direction makes sense within that context. So in their stringy RVM, they have a vacuum which is filled with fields from string theory, such as axions and fields associated, composite fields associated with gravitons. So R mu, the Riemann tensors and Riemann tensor and the dual of the Riemann tensor multiplied together, things like that, which are things which come in gravitational anomalies. So they have found that they could get early universe inflation using the gravitational condensate involving R and R tilde, where R tilde is basically epsilon mu nu rho sigma associated. It's associated with the it's that usual quantity that we have. Okay, so they found that inflation is similar to the Starobinsky-like inflation in supergravity. So they found all of that, and this is not what I'm going to be talking about. But then, as the inflation comes to an end, R tilde has decayed, and then what we are left with is a theory that they have, which is involving the B field, the d mu b, together with the Bx R tilde. Okay, where this Bx R tilde is obtained because of the Green-Schwartz cancellation mechanism. So that's kind of our starting point of our theory, and the RVM, the stringy RVM people also have this as a starting point, but they do all sorts of other things with it. And in particular, you can see from this equation that the B field satisfies is sourced by the RR tilde, and that can have all sorts of interesting effects at later stages, such as leptogenesis and things like that. But I won't go and talk about that. So what we are saying is that once the inflation is over and reheating begins, the universe gets populated with chiral fermions. And these chiral fermions, they produce an axial current, J phi mu, and then you have, if you work out the divergence of the axial current, you get anomaly terms. You get the RR tilde because gravitation is still there, and you get the F mu nu F tilde mu, which is that for the U1 gauge field. Okay, so these are the chiral U1 anomalies. The RR tilde stuff is going to be cancelled by means of the Green-Schwarz mechanism. And so essentially, we will be having diffeomorphism invariance, but we've still got the chiral U1 anomaly. And so this is going to be our starting point for our theory, that we are going to be looking at a gravity model where we have the Einstein-Hilbert term, we have also the term d mu b due to the axions, together with the Chern-Simons term, where we will only be looking at the U1 FF tilde. There could be also the ones for the non-abelian theory, but we're not going to be looking at that. And then clearly there's the kinetic energy F mu nu, F mu nu. The non-abelian theory have instanton topological sectors, and it's a different business. There's also a dilaton in the theory, but the dilaton will be taken to be a constant, which is common in this approach, and it also avoids problems of varying fundamental constants. So the various Chern-Simons operators, as a matter of interest, the FF tilde can be large if there are electromagnetic fields around. RR tilde vanishes on exact FLRW, Friedman, Lemaitre, Robertson, Walker metrics, and it can become non-zero only for chiral tensor perturbations. So if you think in terms of order of magnitudes for gravitational waves, RR tilde is very small, because if you look at it, it's going to be of the order of omega to the fourth h squared times chirality factors. H is like 10, this strain is like 10 to the minus 21, omega is like 10 to the minus 18 hertz. So it's going to be small in that regard. So now we come to the start of our work. So you can see that the model that we had the I'm going to use A because this is the start of our work. It's based on Eichhorn, Gies, and Roche's paper of 2012, and there they have the axion being A rather than B. Our axion with pole B, but to be compatible with that paper, we're going to retain A there. And they have an abelian theory, F mu nu, F mu nu. They didn't have any RR tilde. We don't need that. Sorry. And they also have Chern-Simons terms, F mu nu, F tilde mu nu. Okay. And so as a result, we don't have the gravitational part. We have more or less their model, except their model is in flat space. So this was the starting point of my work with Nick Mavromatos in 2024. We said, aha, this is a model which looks a bit like the stuff that we want to play with, but obviously it's in a flat background, but nonetheless, let's see what it says. And we were pleasantly surprised at some of the stuff we found. And so that's what I'm going to first talk about, and then see how gravity might change the situation. So, now going back to axion electrodynamics, which is relevant for us within our model, you find that the coupling, the coupling here has got negative mass dimension, and so it's not perturbatively renormalizable. So you use the functional renormalization group here deal with this model. And so we following that paper of 2012 by these authors that I mentioned, we look at the flow associated with those couplings. Now, clearly, as I've already stated, this is flat space, so we don't have d4x root minus g, we don't have the Einstein-Hilbert term, and we don't have the RR tilde term. The F mu nu F mu tilde, which is non-abelian, as I mentioned before, can include QCD SU3, and they can give instantons, they can give mass to the B field, but they have instanton sectors, and I'm not going to be talking about that in this talk. So as I said, we will be dropping the RR tilde term, and so we should look at the simplified theory first in flat space. So if you now look at G bar K, this well, have I got it here? Sorry. Yeah. This was the Chern-Simons coupling here. That does not run because of shift symmetry. And so that is important for us. So the renormalized coupling, GR squared, is coming not from any renormalization running of G bar of K, but it's coming from the wave function renormalization of ZA and ZF. And so if you work that out, you will get an equation for the running of the equation is 2 plus 2 gamma F plus gamma A G squared, where gamma F is basically minus d by dt of the logarithm is the anomalous dimension, and gamma A is the anomalous dimension associated with the gauge field, with the axion. So when you do all of that from this paper of 2012, you get this equation. Now, this is an equation, type of equation that you can get in a lot of these theories, especially with theories of the form LPA prime, where you have a polynomial over another polynomial. So that's not unusual. But the interesting fact about it is that the singularities here are actually either real or pure imaginary. And that is not obviously, you can, if you typically look at it at a ratio of polynomials, you won't necessarily get that. So that made us think, hang on, G being pure imaginary and G being real, and there are no mixed type of things with real part and imaginary part. Wow, that could have something to do with PT symmetry. And that's why we thought, hang on, let's investigate this further and see what are the implications. So before I talk any further, I should just say what PT symmetry, at least in a very simple-minded way. So in terms of electrodynamics, you have under PT, E goes to E, B goes to B, and FF tilde is equal to E dot B, and that goes to E dot B under PT. And so here the dual, F dual, is given by epsilon mu nu rho sigma, F rho sigma, and that's how R dual and all of these other things are defined. So essentially, we find that under PT, if B is for B a pseudoscalar, now I've gone to our notation, instead of using A, I'm using B, but please bear with me. We have two different notations for the same thing. For a pseudoscalar B, which is even under T, then alpha B FF tilde goes to minus alpha B FF tilde. So essentially, it is Hermitian, but not PT symmetric. Okay, while the term where you have I alpha B FF tilde it is PT symmetric. The reason why I'm mentioning this is that, remember, in the singularities, we got a singularity where G was going to be either real or G was going to be pure imaginary. Okay, when G is pure imaginary, you'd have a situation where I'm talking about with PT symmetry. That's why I'm talking about PT symmetry here. Okay, that I alpha. So when G becomes imaginary, that would be an example of that. So that's what made us think about PT symmetry, because we've been doing some work on PT symmetry. And we said, well, okay, what has PT symmetry got to say to us about this? So let's just state here the two things. One, we're in Euclidean space, so the eyes appear in different places. So the top one is effectively a the Hermitian case, and the bottom one is the PT case. It's just the way the T goes to IT and all of that type of stuff that happens. Okay, now this is where our input is coming in from the string theory, essentially. This alpha, which we call G mix or G bar, it depends on which paper you look at, okay, which I've been talking about in previous slides. This alpha, because of our string theory derivation, is of the form alpha is equal to √2,3 ms to the minus 2 over 1 over 96 kappa, and kappa is equal to the Planck mass to the minus 1 in natural units. So the Planck mass is 2.4 times 10 to the 18 GeV. ms is the first mass of the first excited string state. Now, the important thing is that in our effective theory, as soon as E approaches ms, infinitely many string modes could start to contribute. So ms does not run. It's like a cutoff for our theory. So this relation that we have between alpha and kappa, ms is going to not be involved in the running. So alpha running means kappa running. And that is a link which we take seriously. It's not the sort of thing that typically you would be doing within your FRG calculations, but within a string theory bias, we are saying, hang on, the running of alpha or G mix, etc., is closely related to the running of our M Planck, and so that's related to the gravitational constant. So that is an important link, and it's you can say it's for us something that we want to take seriously. Okay, so now, as I say, ms does not run. So if you now go and look at this type of the Hermitian theory is on the left, and to the right is the PT-symmetric non-Hermitian theory. And you can see the Hermitian theory has a singularity, and to the left of the singularity, you have a trivial fixed point, and then it goes up, has a singularity, and then on the right of the singularity, you get a non-trivial strong coupling infrared fixed point. On the right-hand side, you get the Hermitian theory, where G goes to IG, and it looks quite different. And you can see here, on the right-hand side, I have this little rectangular box, okay, which I expand out to give you the lower rectangular box. And you can see in the lower rectangular box, there is a infrared fixed point for imaginary G, and also an UV fixed point. And in the upper one, you can see that there is also things run away to a high value of K, to high value for a UV on the top branch there. So what we are trying to say is that somehow the Hermitian theory, where we have the singularity, can jump when we have that singularity. We have some sort of Landau pole, and it could then jump to the non-Hermitian theory, which has a reasonably interesting behavior, which connects the UV smoothly, the UV behavior to the infrared behavior, which you can see in the lower rectangle on the right-hand side. So that's the jump, of course, is something that we can't do rigorously, okay? But nonetheless, this is where it's a kind of intriguing conjecture on our part that something like this can happen. So so when we got all of this, we felt, wow, this is kind of interesting, and this was something that we said, well, okay, maybe if we can put in some gravity, that this picture going to still hold, or is it all going to be overturned? Okay, so that was our concern, and this is the work that we have on the archive from December. So essentially, I've described all of the stuff that is on this slide. We have the various K singularities. Anyway, I've described all of this, and you can actually translate from movement in G to K by looking at the beta function. I know it's slightly confusing. The axes were all in terms of G, and then we're talking in terms of K, but you can write dG by dt equals beta of G, so you can convert your K running to G running, the behavior in terms of G using this type of relation. So now what we say is, okay, is this picture going to be overturned if we introduce gravity? And so we introduce gravity in kind of in a simple way, where we just basically we projected onto the transverse. You know, gravity has many possible components. We just projected onto the TT component, and so within that approximation, the equations get quite simple, and we have a equation that we had before, dTg mixed squared. Now that term, we had a 2 eta A and an eta B term, but now we have a gravitational part minus BGN there, and multiplied by G mixed squared, which was the Chern-Simons coupling. And then we have, in addition, we have the gravitational Newton coupling running dTgn equals 2 plus eta n gn, where eta n is the anomalous dimension associated with gn. So essentially, we have these coupled equations, and then we try and solve them and look for whether the singularity that we found in the flat space is still present. And it turns out, within this approximation, I have to accept that this is an approximation, that within this approximation, the singularity structure is still preserved. And that is kind of exciting for us. That tells us that possibly the features that we're talking about can be relevant for gravity. So here, in a very simple-minded way here, as we said here, we've got our foundational relation between G mix and Gn kappa from our string embedding. So for us, that's an important relation which we take from our string theory framework. So once you do that, then clearly, if G mix goes into the PT branch, G mix goes to IG tilde, and then you can see that G mix squared, which is going to be equal to kappa squared, will give rise to a kappa squared, where Gn becomes less than 0. So in that sense, we get a negative repulsive gravitational behavior, which is different from what people talk about in terms of dark energy and other sorts of things. It's a different way of looking at things. So this is something that actually there is a work by Sarben Sarkar from Oxford, in which he actually, this was some years ago, he thought that the lambda CDM, he wanted to change that to have no lambda, and that the world was living in a void, a very large void. So we could be living in that large void, but I think one of the things about Sarben Sarkar's work and his collaborators is that the fact that he needs a huge void, a gigaparsec void, which may or may not be compatible with experimental observations. But our mechanism, we could work in that void. We could have here a GN which becomes negative through the we don't have a cosmological constant, so we could fit in within that framework and see, and maybe in this way that framework would not need such a gigantic void, but that's something that can only speculate. So now I talked about PT invariance, and the issue of PT invariance is not just making the transformation some coupling multiplied by I, and the model is PT-symmetric. That's just a matter of classical analysis. It's nothing to do with the quantum theory at all. The reason why PT is actually taken seriously this day as a branch of fundamental physics is that it is a way of going away from hermeticity in a serious way. So this is one of a paper that launched PT symmetry from 1998, in which a quantum mechanical Hamiltonian was considered, and you looked at the Hamiltonian, which is of the form p squared plus m squared x squared minus ix to the power n. Now, clearly, if you took n real, n greater than or equal to 2, so for example, if you took n equals 3, you get plus ix cubed, okay, and that is a non-Hermitian Hamiltonian, and you would not expect that the eigenvalues for such a Hamiltonian would be real, but all the eigenvalues are real, and this persists for higher n as well. So this is quite remarkable, and it's not an accident. It's so the whole basis of PT symmetry and an extension where you can get away from hermeticity and look at non-Hermitian Hamiltonians is now fairly well developed. And so in this particular case, P parity here, x goes to minus x, and time reversal, this complex conjugation, I goes to minus I. So Ix to the nth becomes Ix to the nth. And so that is PT symmetry. Certainly not Hermitian, okay, in general. So you have an underlying PT symmetry. But this at the moment is no different from what I was saying before. Why is this important at a fundamental level? Well, if you have Dirac hermeticity, all our quantum theory typically is based on Dirac hermeticity, and we have an inner product which is actually independent of the Hamiltonian, and we find that we have real spectra, we find that probability is conserved, and everything is reasonably attractive and good. So all quantum mechanics is based on that, and QFT has also been based on this. So this is all the physics that we typically know and understand using the Dirac hermeticity. Now, the question is, if you have a non-Hermitian Hamiltonian, what can you do? Do you also have we have a real spectrum? We found a real spectrum in some of these things by actually calculating stuff. But the interesting thing is that if you want to base a quantum theory, do you have an inner product which is conserved? And the answer is yes, in some cases you do. And so the inner product typically could be the Dirac inner product with a new operator, eta, a metric operator, sandwiched between the two states. In general, this metric operator is not universal. It depends on the Hamiltonian that you are considering. And that's, of course, a bit of a drawback compared to Dirac hermeticity, where the inner product was completely independent of the Hamiltonian. But nonetheless, what I would like to point out to you is that if you look at the partition function, and the top partition function is in terms of a path integral, And the second partition function, the lower one, is in terms of canonical formulation, where you have a time-ordered exponential and you have this metric eta. And that metric eta can be quite complicated or may not be easily calculable at all. But nonetheless, based on general arguments, you can show that the Schwinger-Dyson equations that you can obtain from the first formulation of the path integral is the same as the Schwinger-Dyson equations obtained from the canonical version, where you actually explicitly have a metric. So in some ways, the path integral, in quotes, knows about the inner product without you explicitly saying something about it. Now, I'm not saying it is going to be true in all situations, but certainly for single scalar theories, you can show that. Now, you might think that the development of the Wetterich equations, which depend on Z1J, you can then say, all right, we haven't put in an eta explicitly there, but nonetheless, maybe the results that we get from doing the formal manipulations using connected Green's functions, Legendre transformations, etc., starting with the Z of J, will give a set of equations which will permit PT-symmetric solutions. Okay, that is not been proven in any rigor, but I'm suggesting that this statement, which has been proven in rigor and started off with H.F. Jones and Ray Rivers in PhysRev D75, and they had a couple of other papers on it, and then I, with Nick Mavromatos and Alex Soto, have done that in general D dimensions. So to me, that's kind of intriguing. That the general formulations where we get PT-symmetric behavior may not be inconsistent. Maybe it's going to be allowed, but that is not rigorous. So now we come to the conclusions, and I think I've kept my time pretty well. The conclusions is that the stringy RVM model that we obtained from string theory versions also passes a test of so-called the swampland conjecture. This was a conjecture by Uguri and Vaffa, in which say, hey, loads of people produce lots of effective field theories. We think a lot of them are bad. They're in the swampland, okay? And so they have some criteria. I'm not saying that the swampland criteria is rigorous, but nonetheless, we think that the type of stuff that we're doing may not fall into the swampland and may be okay. We don't have, for example, any stable de Sitter vacua required. Inflation is anomaly induced. So that's, at least we think that maybe it doesn't fall foul of the swampland conjecture. The other thing I would like to say is, obviously, when you do this type of FRG, you could have higher curvature terms, and the theories can become very, very complicated, and I'm sure that's what a lot of you professionals are thinking about on a daily basis and worry about it. We are very simple-minded. We did the simple transverse traceless projection and got some answers. At least it's good that we got something which is encouraging rather than being dead right from the beginning. But we realize it's not the end of the story. We could have quadratic terms in the Riemann curvature there, but for constant dilaton fields, which we want, they can be written as Gauss-Bonnet terms, which are total derivatives in 3+1 dimensions. And so as a result, we don't need to worry about them. So what remains are Chern-Simons terms, which is the things that we're talking about. Remember, the gravitational Chern-Simons terms we got rid of from the arguments that I gave earlier. So then there are a couple of other things I'd like to mention, and this is I don't know, this is something that people in the FRG community know more about, but there are some, I have heard mutterings about concerns about the meaning of beta functions calculated using the as changes in k, where k is what happens in Wetterich, the cutoff. And they say there's no physical meaning of the running of the gravitational couplings using this FRG formalism. You should really worry about actual momentum dependence of observables on using external momenta. Now, there has been a recent paper in this regard by Buccio and Donahue, and actually one person from the FRG community, Parachi. So they have things to say, but I don't know really what to say about that. I'm aware that there are some issues like people talk about. Then our approach, because we have a conjectured phase transition of repulsive gravity, and this has physical consequences, it's a bit different. And so we may not be falling foul of the criticisms in PRL, but again, ours is a conjectured relationship, so we can't say it's very rigorous. But I can only say is that my co-author, Nick Mavromatos, did some work on this in 2011 with John Ellis. And so he tells me that he doesn't think his earlier criticisms apply to this work. So that at least makes me feel somewhat better, but that's not a scientific reason as such. But nonetheless, I'm encouraged by what Nick tells me. Okay, so thank you very much for listening. And I'm very glad that I managed to keep within my 45 minutes and not take up too much of your time.
All right. Thank you very much, Sarben, for the nice talk.